Hello everybody, and today I'll be just showing like 3 years of the same project that I've been trying to do. Overall, the idea was being pretty simple. To the open source, easy to use LED controller. However, something went terribly wrong. Now you will be seeing the raw part I needed to finish this project. Initially, idea was pretty simple. Buy an already LED strips kit, actually install it, and just use it as a normal people will do. However, something went terribly wrong because an original controller requires some sketchy app that requires all your permissions, and I decided to not install it. On the first look, very simple, just to connect to the UART pins and just program. However, it's not so simple. It's ESP32 modified version, so it will be not flashing like that. Unfortunately, I can't flash this unit. The requirements for prototype 1 was simple PCBs that can be done in university, ESP32 based, and it should drive one RGB LED strip that I already have, so it should be powering for 12 volts and doesn't ask for another power source. So I started to make my first prototype. Very fun detail I figured out on my PCB board that I made for prototype 1. As you can see, there's an official documentation for this board. And as you can see, the last pin is power on a documentation. However, on an actual board, it's not. The lesson learned: always check footprints before doing the boards. Dump error counter +1. Another issue I found is that I basically shorted all channels to do one control link. Yes, very stupid, but what I can say? Dump error counter +1. So I quickly made a frequency test and realized that I really need to move on. However, I needed to create another prototype, but this time I completely changed the idea. Instead of using microcontroller on a board, I created a pin header where everything will be connected, and I hope this version will be working without any issues. However, something went terribly wrong. As you can see, I figured out to use Litchi board and run Linux for this controller. However, I quickly realized that all documentation for this board was being very bad and written in Chinese, so I was being unable to run Linux on this board. So my skills was being not enough, so I decided to switch to another microcontroller. Initial idea was being it consisting of 3 boards: microcontroller, PCA chip, and amplifier board that will be send signals to the LED strip. However, this idea was being not really good in realization. When I soldered everything together, it was being really flimsy, too many wires. You can make many mistakes while soldering them. So I decided to do one board that will have one microcontroller and will be just doing its thing. However, before we go for the prototype 3, here will be a short message about 3D printing case for this prototype. Actually, I have some mistakes in the PCB and imperfections in design. I decided to 3D print a case for these PCBs. It's very special for me because it's my actually first design of case. Unfortunately, I didn't have time lapse of doing it, but from the first go, I managed to fit all electronics inside. It has some mistakes like small holes for the cover and things like that, but it works. There's nothing too much to tell about Prototype 3, except I decided to remove PCA extra board and install this PCA chip on board. Also, instead of using separate transistors, I use an IC that has these transistors inside. However, still, I didn't use the microcontroller on the same board, so we go for Prototype 4. The reason why I didn't install a microcontroller on a Prototype 3 is because I just wanted to do a small debugging board where I can mess around, check chips, check actually my schematic, and then I can install microcontroller on top of it, and I will have working project. And in a prototype 4, I'll be just finish that, wrapping in one PCB, and it will be nice looking. However, something went terribly wrong. 32C3 chip as a module and created single LED PCB, but I separated an logic part from actually power part I've done before. However, I've done this PCB at home and there's been too many cracks in the traces, too many issues, and the most importantly, I forget a WLED 3.3 volt chip, so the board didn't boot at all. So I decided to put this project on the shelf and take another look after some time. One thing I figured out while doing this project, exactly prototype 4, it absolutely makes no sense to do PCB at home, except it's something very very easy, like just 3 resistors and 2 capacitors. In other cases, it's just easier to order them from juicy PCB and just get the very good professional PCBs. And again, unfortunately it doesn't sponsored by juicy PCB. I really wish to, but not. So the year passed since last things I've done for the project. So I decided to start completely from the scratch, so taking my Kindle, take my favorite drink, it's cappuccino, sat in a coffee shop, and started write any constraints for the controller from complete scratch. Well, the controller should use popular chips that are supported by WLED or ESP now. Also, be powered for 12 volts straight away, and third thing, should control one RGB LED analog, one white strip analog, and 2 digital strips. Let's quickly talk about our final prototype design and the PCB and some schematical decisions. So, first we have a connector, capacitors, and we have snoot, because we have a chip in a 219, which will be actually measuring current and voltage on an actual controller without being consumed. So it's important to have this snoot. Then we have an XL1500 chip, which is DC-DC converter, and it basically takes any voltage from 40 volts and turns it to the 5 volts and actually uses in a PCB board. As it's a DC-DC converter, it requires a coil and a couple of diodes for working, and of course a couple of capacitors for removing all noise from there. Then we have an MS 117 3.3 linear stabilizer, which turns 5 volts to the 3.3 volts, and is basically being used only for powering ESP and some low power chips. I think it's possible to do design like this. It's not a huge voltage drop over there, and there's not a big power consumption. So I think in terms of heat dissipation, it will be fine and will be working for a long time. Then we basically have our brain, which is ESP32 microcontroller, which basically performs all calculations, all stuff, and more importantly, it supports WLED and it supports ESP Home software. So we're running this software on this board by using ESP32 microcontroller. Moreover, I've decided to not do any complicated designs in terms of MOSFETs and just bought special MOSFETs that have a logic gate that works with a voltage 3.3 volts. And it works seamlessly, so I don't need to do any adjustments. Then I have a temperature chip, which is DB18B20, which is basically for checking temperature of the MOSFETs, not to burn anything. It's just for safety, like safety feature. And then I have CH330 chip, which is basically USB to your converter, so I can connect just USB cable over there and flash controller. There's also one great cardinal of this controller, which can be seen from the first look, but it's very important. As we are using the 2 digital strips, which are importantly using 5 volts For logic level, we need logic level shifter, as ESP32 works with 3.3 volts logic level. So I have using an chip SN78NC and a lot of letters over there. I think you can read it from the screens, which is amazing chip. I never have any problem with that, and everything works seamlessly. It's pineapple on pizza. It's tasty. Well, I would agree. I'm sorry for every Italian watching this. One more design thing that I've done for this project is that I have a couple of jumpers over there, like jumpers over resistors. So here you can see it's pull-up resistors for I2C and they're optional. If you don't use any I2C devices, no inner chip or OLED screen, you can just not install them. Moreover, R20 will be short DC-DC converter. It's important. For example, you need to work a 5-volt version of this, when you can just take a 5 volts and go to the IMS chip. Or, for example, if you need that DC-DC converter, you don't use any digital strips, and you need just DC-DC converter to have an output 3.3 volts that will go straight away to the chip. You can actually pass through an IMX chip by setting out 19 resistor. I think it's a very good idea because even me needed to have an version of this controller that works for 5 volts, and I installed these resistors, and without redesigning much PCB, I was being able to do it. Basically, it's actually been passing something like 3 weeks.
Hocus pocus, there's pizza on your focus.
And last computer aided design will be finished, and as you can see here, actually any PCBs arrived from factory, and only thing I need is to find the time when I can solder the PCBs and to check if that is working. But unfortunately, I'm so busy with assignments and deadlines.
1 week later.
So first things we need in the morning is a cup of cappuccino. So I'm thinking, I could go for never today. I'm feeling fancy. Why not? Engineers are also humans. Yeah, let's grab some good graphic in the never. It's expensive. Yeah. It's early in the morning and I really need my cappuccino. And while you're watching me soldering an PCB board in a time lapse, I just wanted to say thank you to the University of Kent for this awesome lab. And secondly, I wanted to say big thank you to the Nathan, my project supervisor, which helped me a lot during the understanding why DC-DC converter is not working. And we'll be talking about in a minute. But before, it's short interview with Nathan. Yes.
I'll take a picture if you want.
How should you introduce you like?
I don't know. Teaching fellow in engineering. I know a little bit about electronics, to say some.
So yeah.
I'm Alex's supervisor. He does very good work.
Thank you.
Made a few of his own PCBs, which are quite impressive nonetheless. We don't have very many students that get to this stage anyway, so it's very good that he is at that level. So yeah, your PCBs for the project will be really good as well. I've seen them. We'll get them made after Christmas. There's not enough time. We'll do it before Chinese New Year, so they will be arriving before the whole country shuts down, which is good. I think it shuts down for about 2.5 weeks, so we should account for that. But yeah, no, it's good. It's good to see.
Brilliant. Thank you very much. So yeah.
Sorry, buddy. Anytime.
So, the issue with the chip and why the DC-DC converter will be not working can become very clear if we head look to the datasheet. The datasheet states that pin 4 is enable pin. Drive enable pin to low to turn on device. Drive it high to turn it off. What I'm doing in my schematic. So I'm using resistor R7 and I'm connecting it to the input power. Why it's not working? Just because the pin is driving high. And even the schematic will be show you that you're doing something wrong. You see this bar, it says inverted pin. Why, and one more time, why connected it to the power? Number counter +1. Thanks God, the fix is very easy. In a new revision, I've just connected it to the ground, but in a revision I have now, I just didn't install R7 and everything was been working fine. So I have an board here and a cool LED display. Just see what happens if I power it up. For some reason didn't show consuming current, but it's alright. Shouldn't be a lot. How to run it in a programming state. So basically just short this leg to the ground and it works. And it just connects to the programming state and you can flash it. Here and Alex from Future. And I'll be quickly explain what was been happening in 2 clips before. So in the first clip, the board is successfully flashing. However, it doesn't boot up. And as you can see carefully, we have a pin header here, which has pin 8 and 3.3 volts, and we have jumper here, which connects. And it's a requirement for flashing. However, one thing I forgot, and I didn't know about it. Honestly, I would say I didn't know, but I should read the documentation more carefully. So dumbbell counter +1. But is that in a GPIO 9, it should be go for weak pull-up in terms of booting microcontroller. So we're going to the keycard and have a look what we have there. And we have channel 3 on it. And we have 2 resistors there, R12 and R13. And R13 is connected to the ground. And it brings this weak pull-up to the ground, so microcontroller doesn't boot. So I went with a simple workaround. As you can see, I just appended any capacitor there. What happens? It connected to the 3.3 volts with a plus leg and to the ground to this resistor. So when the board is connecting, it starts keeping in a charge and puts this pin to the pull up so the microcontroller can boot. And here are some very nice updates. First, I can see milliamps, so it's 4 milliamps consuming from the power supply, which is awesome. Second update. Hello buddy, you're working now. So it shows temperature from the sensor. The reason why it wasn't being working is I have error on a split screen. It should be pin 3 going SDA and pin 4 is going escalator. God. No error counter +1. Don't look at my table, it's really messy now. But, damn it, it's working! Finally! Gosh, it took me too long to finish this project. But damn it, it's working now. Amazing. In terms of software, it's pretty easy. I just taking an open source software called WLED, create its fork, and just appended in a small function in a main file that will be taking data from temperature sensor and current sensor, and actually was being displaying them on a small OLED display. Also, it was being fetching an IP address and displaying it on a display. It was being a couple of hours job, which is not complicated. And thanks ChatGPT for helping me. And then I opened Fusion and just starting and drawing a case for this project. I'm not a mechanical engineer, so don't judge me for that box. But I can find all parts online that I was being using, 3D models. So it was being a big deal to make all holes correctly with all precision. And I was being made in a case for this project and send it for the 3D print. One mistake I make actually all walls 1 millimeter, and the case was being too flimsy, so I reprinted it later. Finally, we have our 3D print done, so now we need to collect and finish build in a case. Thank you very much to the company called Creality for this awesome printer. It's not a sponsor, but I bought it actually, but it's a very nice printer. It's just easier to set up that guy Samsung printer, which was being required a lot of suffering with the driver. So yeah, 3D printers nowadays are pretty much easier than actually the normal printer. Here we have our stands. But it feels so wrong that I'm doing it, but damn it. So you got it absolutely right. I 3D printed 8mm stand, so the PCB now fits perfectly and connector outputs where it should be. Don't call me nerd, but I am. As you can see, here we have our project finished. So here it's in a controller with a screen, it's connected to the LED strips, its controls, and now here will be a short demonstration. So I can switch an RGB LED, for example, to the different colors, to the blue, for example, or green, or things like that. I could control like how bright LEDs are, like this or something like that, and I could install different effects on it. So it's everything that's supposed to be in a simple WLED software, like in a classic vanilla WLED software. So it works, and I'm very happy that this project is coming to an end. I didn't have any ideas how I can improve my controller by now, but hopefully you write down them in a comment and I will be doing improved version of controller based on a comment. It could be in a video on the channel. However, thank you very much for watching this video and joining this long part. However, it's time to say goodbye, and I really hope I earned your like and subscribe. Thank you very much for watching, and goodbye.